Uh, So welcome everybody. This is the first ECR presentation of 2024. So welcome and Happy New Year to everybody. Today we have the presentation by Dr. Alec Linot on data-driven prediction of vortex dynamics and hierarchical graph neural networks. Uh, Let me introduce him to you. He is a postdoctoral researcher with Professor Kunihiko Taira in Department of Mechanical and Aerospace Engineering at UCLA. He received his BS in Chemical Engineering from Kansas University. His PhD is in Chemical and Biological Engineering from University of Wisconsin, Madison. In his PhD, he developed machine learning techniques for modeling and controlling turbulent flows. His current research is in modeling, control, and stability of chaotic dynamical system. Chaotic dynamical systems are deterministic systems where small perturbations to the system result in dramatically different dynamics over time. So just a few things. If you have any questions, please enter it into Q&A section. And Dr. Linot will take over those whenever he feels like. So without much ado, let's welcome Dr. Linot.
Okay, thank you for the introduction. As mentioned, today I will be discussing data-driven prediction of vortex dynamics with a hierarchy of graph neural networks. And with that, I will begin my talk. So the motivation for this work is much of my work revolves around trying to predict fluid flows. And the motivation for this is you might want to predict a flow in order to control it, or it might just be desirable in order to make predictions in order to forecast future events. And so these flows can come at many different scales. And so here I'm just showing a few simple examples of that. On the left, this is just flow in a channel. In the middle here is an example of flow over an airfoil at high Reynolds number. And then I'm just showing a geophysical flow that's very large scale here on the right. And as I'll get into, modeling these systems can be very expensive. And so the aim of this work is to see how we can use machine learning and the large amount of data we have on many of these systems in order to accelerate the simulation of these sorts of systems. Okay, so the outline for my talk is going to go, first, I'm going to motivate the use of reduced order models for speeding up computation. Then I'm going to explain why graph neural networks can be a useful way of building these models. And I'll explain how we build graph neural networks for vortex dynamics. And then finally, I'll discuss how well we perform at actually predicting some examples. And as mentioned, please feel free to ask any questions throughout the talk. I have about 30 minutes of material, so there's plenty of time for questions, and I think it'll be better, if you ask them during the talk. Okay, so first, let's motivate the prediction of these fluid systems using reduced order models. So typically, the way that we go about solving problems with fluid flows is we solve the Navier-Stokes equations. And in particular, we tend to solve it often on a discretized grid. So the typical way this would work is we would have a very finely resolved grid, like I'm showing you here on the left. We would have some initial condition on this grid. And then we would do something like finite difference to discretize the Navier-Stokes equations and evolve this initial condition forward in time, like the little example here I'm showing on the right. And as I mentioned before, the challenge with this is when your scales become very fine, when you have very complex geometries, this sort of thing, these computations get very expensive because you need very fine discretized grids. So one way of reducing the size of this problem is what in the fluids community we refer to as reduced order modeling. And the general idea of most reduced order models is that you take some state representation U, where all U is here is it's the velocity defined on all of our grid points. You reduce the dimension somehow. Here I'm writing in code, which would be the machine learning way of putting it. And then you evolve this low dimensional representation forward in time. And then finally, you decode it back to get your full state. And there are many, many ways of doing reduced order modeling in this fashion, but just a couple very common ones that I would like to highlight. Here, the classical way of doing it would be principal component analysis and Galerkin projections. And in the fluid community, we'd refer to this as proper orthogonal decomposition. PCA has many, many different names. But the idea of modeling in this fashion would be to do your dimension reduction linearly, and then to predict the dynamics by projecting the equations of motion onto the PCA modes. Another option that's become more popular for reduced order modeling recently is using autoencoders and neural networks. And so how the reduced order modeling would look like in this fashion is you would have a neural network that takes your data on your grid, reduces it to a much smaller dimension, and then you can find an evolution equation in this lower dimensional representation, both using neural networks. And I'm not going to talk too much about neural networks, but the general idea behind neural networks is they're just function approximators where you optimize weights of the neural networks in order to minimize some loss function. And so these reduced order modeling approaches and many others are very popular in the fluids community. But some drawbacks typically you run into when doing reduced order modeling in this sort of fashion is that often your state variable, you might need the full grid of information, or even if you're taking sparse samples, typically your state exists on a grid. And also, when you do reduced order modeling in this fashion, you cannot change the dimension of the state very readily. The neural networks, or just even this linear dimension reduction, often you just have a fixed state size. And so instead of doing modeling in this fashion where we have data that lies on a grid, another alternative way of thinking about doing the modeling is in terms of coherent structures. So instead of talking about modeling the velocity at every point along a grid of a simulation like this, an alternative is we can instead think of modeling the interactions between the vortices in a simulation like this, shown here at the left. So if we can do modeling in this fashion, we can reduce the problem down to just the number of vortices that are in the simulation, and then all we have to do is model the interactions between these vortices. And here at the right, I'm just showing you, there's a nice review article by Haller where he talks in more detail about what coherent structures can look like. But for our purposes, all you need to think about when I'm referring to these coherent structures is vortex cores, like I'm showing you here in the simulation to the left. So there are some models that just directly model vortex interactions like this. So you can model point vortex dynamics by using this equation that's called the Biot-Savart law. And here at the bottom, I'm just showing you a simulation of what it looks like when you model, in this case, it is the evolution of point vortices behind a plate. Also, are the videos very laggy for people, or are people seeing the videos? They're kind of laggy for me.
I think the visuals are okay. Yeah.
They're okay? Okay, thanks, John. Okay, so here in this video, yeah, what you're seeing is a plate being dragged to the right, and you're seeing a bunch of point vortices that are coming off of it. And this sort of captures the correct dynamics behind this flat plate. And instead of having to model it using a discretized grid, you can instead model it as just these set of point vortices. And I would also just like to shout out that it was Luke Smith in our group that did these simulations shown here. So the goal of this work that I'm going to present to you is, well, instead of trying to predict the dynamics of data on a grid, can we instead predict the dynamics of a set of point vortices like are shown in this simulation? And in particular, whereas in the previous simulation, I was showing you this flow behind a flat plate, what I'm going to look at first as a nice test case is I'm going to see if we can just predict the dynamics of a set of vortex clusters using graph neural networks. Okay, so that is just the first part on reduced order modeling in general and why we want to use graph neural networks. And I just want to emphasize that, again, if I was trying to model a set of point vortices using some of these classical methods, I wouldn't be able to do it because you can't add new vortices into the simulation and use these classical reduced order modeling methods. Whereas these graph neural networks that I'm going to talk about, we will be able to insert new vortices and new clusters at will. And so that's what I'm going to talk about next. I'm going to now talk about graph neural networks in general, and then how we can use graph neural networks to predict these point vortex dynamics. So graph neural networks have been used to make predictions on many different sorts of complex problems that can be described as a graph. So here on the left, for example, I'm showing you one use case for it, which is you can take molecules, you can build a graph that describes this molecule, and then you can use graph neural networks to do things like predict molecular properties, for example, like smell, taste, or more industrial relevant properties like whether or not it'll be soluble in something, this sort of thing. And another wildly popular use of graph neural networks is for point clouds using this graph neural network called PointNet. So on the left with the molecule, there's sort of a clear graph just described by the molecule. On the right here with point clouds, what you can do is you can take, for example, 3D point clouds of data. You can then form a graph connecting the data in this point cloud. And then you can use that for things like classification, for segmenting parts, or for semantic segmentation. So these are some of the popular uses of graph neural networks. And as I mentioned, we're going to use it to try and predict vortex dynamics. So let me describe what exactly the graphs will look like in our case. So here, I'm just showing you an example of a fully connected graph where each of the nodes is going to be one of our vortices, and the edges connecting them are the interactions between those vortices. In our case, what I'm going to use is at each node, there are going to be 3 values. Kappa, which is the circulation. This is basically just how much the vortex is causing rotation. and then X and Y, which are just going to be the spatial locations of that vortex. Then there are going to be edge weights connecting these vortices. And I'm simply going to take the edge weights to be 1 over the distance between the vortices squared. And the objective will be for us to take this graph of the vortices and to predict the time dynamics of the vortices. So this is just dx dt, dy dt for all of the vortices. And the way that we're going to make these predictions is we are going to perform graph convolutions on this graph. And what this means is that we're going to take this graph and we're going to generate another graph, another graph, another graph, until finally the last graph that we're left with will have nodal values dx dt, dy dt. And the way that these graph convolutions are going to work, in my case, is I'm going to use what are known as these graph convolutional skip layers, where here X is a matrix of our nodes times the number of features, which, as I mentioned, is just these 3 values. L is the graph Laplacian, which I'll discuss more on the next couple slides. But the size of L is just the number of nodes, number of vortices by the number of vortices. And then finally, the thing that we're actually going to be learning are these weights, W and V, which have the shapes, the number of features of X by what I've denoted here is just the number of hidden layers. So we're going to use this in order to increase the number of nodal features in our graph as we move along, and then to decrease to 2 features. And as I mentioned, W and V are the things that are actually going to be optimized during training. And the objective will be to minimize this loss, which is the difference between the time derivative of the true time derivatives and the predicted time derivatives. And so that's going to be our objective. I just received a question in the Q&A, which I'll answer now. So Brenner asked, do you think that using graph transformers could be beneficial? My rationale is being that since you're using a fully connected graph, maybe not all connections have the same relevance, and a graph transformer might account for that. So I think this is a good point. So far, I'm just presenting what the fully connected graph looks like. In the coming slides, I'm going to show the actual graphs that we're working with, which are not going to just be fully connected graphs. But I guess as a starting point, we wanted to just start with sort of the simplest graph convolutions. But I do think that it would definitely be worth us considering different forms of graph neural networks. I tried many different types of graph neural networks. I've been using PyTorch or Torch Geometric so far with that software. But I don't think that we necessarily are using the optimal graph convolutions at the moment. So I think it's a very good point, something to look into. Okay. Yeah, and feel free to keep asking questions. I appreciate it. Okay, so now that I've just briefly described the graph convolutions, let me give it in just a little bit more detail so that people who've never seen this can understand fairly well. So this is what the graph convolutional layers look like here at the left. And as I mentioned before, how this works is I'm going to start with a graph that just has 3 nodal values and edge weights. And then every time we do a graph convolution, it's going to change the number of nodal values. And in our case, we're not going to change the edge weights. So we're just going to get a new graph every time we do a graph convolution. And we're going to have a set of some X number of values on this graph. And then finally, at the very end, the last graph convolution will just output 2 values, which again are going to be the time derivative, which is what we're wanting to predict in this case. And the whole reason that we can have a variable number of nodes in our graph is because in this graph convolution, we are using what's known as the graph Laplacian. And the graph Laplacian is a matrix that is just the difference between the degree matrix and the adjacency matrix. Because I have an undirected graph, it's already symmetric. And all the degree matrix is it's a sum of the edge weights into a given node. And all the adjacency matrix is it's just going to be our edge weights in this case. And just to very briefly show what this graph Laplacian looks like, here I'm just giving a very simple example of a graph where we can look at the degree matrix, the adjacency matrix, and the graph Laplacian. So if we have this graph up here at top with the weights on each of these lines, the degree matrix gives us again, the number of weights coming into a node. So node 0 here has 1, 3, 6 values. So that has a value of 6. Node 1 has 1 weight connected to it, has a value of 1. And then if we look at the adjacency matrix, 0 connected to 1 has a value of 1, 0 connected to 2 has a value of 2, so on and so forth. That's all that's being done to compute the degree in the adjacency matrix. And then the difference of those simply gives us our graph Laplacian. So hopefully that's fairly straightforward. Okay, so now I want to talk about how we can take these graph neural network structures and build a hierarchy of graph neural networks. So this is sort of the main idea of this work. So with our set of vortex clusters, we know that within a vortex cluster that the vortices will be interacting strongly with one another. But outside of it, the clusters will be sort of weakly interacting with each other and causing the time derivatives to change on slower time scales. So instead of building a fully connected graph, we can build two different types of graphs, which I'll refer to as an intra-cluster graph. So this is just a local graph of a given cluster. So we have one graph, in this case, of our one cluster of vortices and another graph of our other cluster of vortices. And then we have an additional node that is representing the mean of the other cluster. So it's the sum of all of the circulations and the two mean values that represent this mean node. So we can define this sort of intra-cluster graph. And then we can also define an intercluster graph, which defines the interactions between this mean nodal value and all of the values within our cluster. And so this should capture sort of these long-range interactions that the nodes within a cluster will experience. And so what I mean in this talk when I'm saying we're doing hierarchical modeling is I'm saying that we are going to be building two graph neural networks over each of these different levels and adding them together. So specifically what this looks like is I will take these graphs that define the interactions within a given cluster. Both of these graphs, I will perform many graph convolutions over them. And then I will also take the graph that defines the interactions between a cluster and the mean, the centroid of the other cluster, and I'll perform many graph convolutions over that. And then at the end, we will add both of these together, and that will give us an output that is sort of this hierarchical solution that predicts the time derivative of all of the nodal values. Okay, so that's the idea. I guess, are there any questions about that so far? I'll sort of show this again, but the idea is just simply instead of making a fully connected graph neural network, we know that the mean value of one centroid should have a specific interaction on all of the nodes of the other cluster. And so by constructing it in this hierarchical fashion, we'll be able to explicitly enforce this type of interaction. And hopefully it should make learning these interactions easier than if we have a fully connected graph. Okay. Yeah, so that's the idea. And now I want to show you how it performs at predicting the dynamics of a set of clusters of point vortices. So the first thing that I'm going to do is I'm just going to consider only 2 clusters. And then later on, I'll consider when we have multiple clusters and many different sets of vortices per cluster. So in this first case, I'm just considering 2 clusters, and there's only going to be 6 vortices per cluster. And I'm going to train on 100 different initial conditions. And the trajectories that I'm using are actually fairly short, but I'll show predictions that are a little bit longer. Okay, so this is the training data. It's going to just be the spatial locations of these vortices, and we want to predict the time derivatives. And there are 3 different setups of the graph neural network that I'm going to compare. I'm going to compare this hierarchical approach that I mentioned before. I'm going to compare that to a fully connected graph. And then finally, I'm going to compare it to one with just the local connections and none of the interactions between the mean centroid, the centroid and the vortices of a given cluster. So what I did was I took that data and then I trained 3 different types of graph neural networks using those different graph setups. Here on the left, I'm just showing basically what the graph architecture looks like. Again, just to emphasize, I start with these 3 nodal values. I perform these, basically they're just the graph convolution, the convolutional skip layers that I mentioned before, but in particular, it's from this paper shown here at the bottom left. They're called ARMA convolutions, but I've simplified it basically so that it's just the equation that I showed you previously. So I perform 4 of these convolutions. Each time the hidden graph is what I'll refer to it as, has 64 nodal values for each of those convolutions. And then finally, I just have a linear operation to go from each of these 64 nodal values back down to the 2 values that predict the dynamics. And then just to remind you, the loss that we're trying to minimize, again, is just the difference between the true right-hand side of the dynamics and the predicted right-hand side. And here at the right, I'm just showing you what happens when I train these 3 different types of models. The blue is the fully connected network, green is the locally connected network, and red is the hierarchically connected one. And you can see that the hierarchical network performs the best out of the 3 during the training. And one thing I would just like to mention, though, is that the fully connected network, in theory, should work, but it just seems that trying to learn both of these different scales of connections appears to hinder the training performance in this case. Also, it's very interesting that the locally connected network appears to train as well as it does. But on the next slide, I'll show you that even though the training error for the locally connected network is quite low, that the predictions will be poor because it has no information about the neighboring clusters. Okay, so this is just training error for basically a single step. But in order to really test the performance of these networks, I'm going to put them into an ODE solver and evolve it iteratively forward in time. So here on the left, I'm showing you the short time prediction of the true data in black. Just to emphasize, this is on test data that the model had never seen. And the prediction with this hierarchical graph neural network method that I mentioned previously in red. And you can see that over short times, the X is the initial point and the dots are the final point. You can see that over these short times that it tracks fairly well, and the dots at the final time tend to lie near one another. Of course, at longer times, these errors start to accumulate, and it's sort of difficult to see, but in this trajectory at longer times, you can see that the points do not necessarily lie close to one another. The vortices don't necessarily lie very close to one another at long times. But even over these longer time horizons, although the vortices within a cluster need not lie on top of one another, we do expect that if the model is performing well, that the centroids will more or less land at the same point. And so here at the right, I'm showing you the trajectories of the centroids. And again, what we can see is that the hierarchical model in red does a very good job in this test case of matching the location of the centroid, whereas the fully connected model here does an okay job, but it is further away. And the local model in green doesn't move at all. So despite the fact that it had a very low training error, because it never sees the interactions of the other cluster, it never moves, which is good, or at least agrees with what we might expect. So this is just for a single example, though. And just to show you that the model works, and I didn't just cherry pick an example, here I'm showing you ensemble averaged quantities. So here I'm on the left, I'm looking at the average error between the vortices, all of the vortices averaged over something like 100 initial conditions. And again, you can see that the hierarchical model performs the best. And in this case, the local model and the fully connected model start to diverge. In particular, I would like to point out that the reason that the fully connected model here is performing so poorly at long times is just because in many of the cases, what was happening with the fully connected model is vortices were shooting off and then just going off into infinity. And so when the vortices break off and start moving away, the errors start to accumulate, and that's why the error here is so high. Additionally, we can also look at the performance of the centroid tracking, which I'm showing you here at the right. And you can see that the ensemble average of the difference between the true centroid location and the predicted centroid location is very low for the hierarchical model. And again, for the local and the full model, it diverges very quickly. And so this is showing you that we get like an order of magnitude improvement in the centroid tracking using this hierarchical model. Furthermore, the other benefit of modeling in this hierarchical fashion is now our network is, our graph is sparse. And so here, what I'm showing you is how that improves compute time. And what you're seeing is the compute time for a single forward pass of the graph neural net when I put 100 vortices in each of the clusters, and then I increase the number of clusters. So here, I'm sort of pushing the models to their limit. I'm adding many more vortices and many more clusters than I was in the previous case. And what you can see is that as we increase the number of clusters, the local model and the hierarchical model tend to scale in the same fashion. Whereas the fully connected model has a much scales much more poorly than those two models because of all of the connections in it. And so we get orders of magnitude improvement in the compute time if we're modeling in this hierarchical fashion, along with the excellent tracking that I showed you. Okay, so that was just for 2 pairs of vortex clusters. But I said that I also wanted to test it out on a more difficult data set. So here I'm now going to show you what happens when we train on a more diverse data set, where the data set consists of 2 to 5 clusters, each containing 8 to 18 vortices. And I'm going to randomly select these for 100 different initial conditions. And then I'm going to show you how well it performs on test data. Okay, so I did this, and I trained the exact same graph neural networks. And here you can see the performance on some on a test data example with a different number of clusters and vortices that were never seen during the training. And here on the left, you can see the prediction of these 4 clusters through time in the true simulation. Here in the middle, this is our prediction using the graph neural networks. And then at the right, I'm showing you the centroids. So data is the solid lines and the dotted lines are the hierarchical model. And you can see that the hierarchical model, even when we've added more clusters, more vortices, and are looking at a combination of clusters and vortices never seen by the model, you can see that the hierarchical model does an excellent job of tracking these centroids. And yeah, and so far, I've just looked at a few single trajectories for this model, and I'm currently in the process of trying to also get ensemble average quantities for this model. But so far, it appears that this hierarchical model can also do an excellent job when we add many more clusters and vortices past the 2 that I showed you previously. So with that, the last 2 things that I would just like to mention are we have a lot of things, moving parts already in building this hierarchical model, but there are some additional problems that still need to be addressed. The first problem is the fact that if I take a vortex cluster and I translate and rotate it, I would expect that that cluster's dynamics would also be translated and rotated. So currently, I'm in the process of working on implementing a method of applying equivariance to the dynamics so that the graph neural network will always output the rotated and translated dynamics as expected. And then the other thing that needs to be addressed in this modeling is when vortices collide. So the other next step is we're going to have to properly figure out how to identify when clusters merge and when clusters separate in order to use this method. And so with that, I'm going to conclude. The main conclusions are that we can use graph neural networks to accurately predict vortex dynamics, even when we are changing the number of vortices in the system. And as I mentioned many times, this is something that classical reduced order modeling methods tend to not be able to do, at least normally. Furthermore, I showed that if you build these graphs in a hierarchical fashion, the predictions are both more accurate and faster than if we try and build a fully connected network. And then lastly, what I showed you in the final slide was just that even though I primarily tested it on just 2 clusters, that we can extend it to many clusters and many vortices, and those number of clusters and vortices don't necessarily need to exist in the training data. Although I haven't yet tried extrapolating it to more vortices and more clusters like outside of the training data. For example, I trained this between 2 and 5. I should now test it to see how well it will perform on 10 clusters, for example. And in the future, I'm working on now applying equivariance, or trying to guarantee equivariance of our outputs. And then also we're working on putting in vortex detection and also accounting for vortex collisions. So the last thing I'd like to say is I just want to thank everyone in my group. And with that, I'd be happy to take any more questions. Thank you. Yeah, Bryn, you want to unmute?
Hi.
Hi.
Yeah. So first of all, thanks for the talk. Very interesting topic. I just have a few questions that, so for example, to advance the simulations, the step, the ODE solver that you use, are you using something like just an Euler step, or is it something fancier?
No, I mean, it's fairly basic. I'm just using, I've tried out a few different schemes, but so like these results here, this was using, it's just ODE 45 in MATLAB. It's the same as that. It's the Dover 15 scheme, which is like an RK4 with an adaptive, it has like the butcher table and that sort of thing. But I mean, it is a very good question, because if I do change the time stepping scheme, I mean, of course, the dynamics will be slightly different. And so it is an important thing to think about. But right now, in particular, since I'm just outputting the right-hand side, there's not really, even if I am doing bad time steps in training, for example, the right-hand side is still going to be correct. So I'm still learning like the correct thing, even if the vortices might not necessarily be placed in the correct locations. Yeah.
I see. And during the training, have you considered, it's just because I'm remember from a paper from, I think the title is Mesh Graph Nets, is that basically they are also trying to use graph networks to model some systems. And some of the systems that they modeled were fluid systems, like a 2D cylinder or a compressible flow over an airfoil. And one thing that they used that really helped a lot was to actually use a bit of noise during the training, because when you advance the simulations based on the predictions from the own model, using a bit of noise during training would kind of help the model to recover, so the error would not build up. And although it seems just like a simple thing, it actually is something that, at least with their framework, things would simply just not work if they didn't add any noise. So I was just wondering if you need to add some noise during training or not.
Yeah, so currently I'm not adding any noise during training. Yeah, so it sounds like what you're suggesting is that it improves training, because also like people care about noise, of course, because the experiments or simulations, you may have noise in general that you need to account for. But yeah, for training performance, I haven't thought about whether or not noise would help, but I'd be very interested. What's the name of the paper?
I can send on the chat in a bit,
Yeah,
exact the name. Yeah, because the idea was that it actually doesn't make that much of a difference when you think about just like a one-step error. But it's when you think about multiple steps, and it's just to, let's say, increase the training distribution, let's say it that way. So the model would be a bit more robust to, basically a bigger distribution, right? Like you would encompass more situations in the training data. Basically, that's the motivation.
That might be something useful, because right now I'm just predicting the right-hand side, but of course it's a little bit more desirable to have like snapshots of data that are separated some apart, further apart in time, and then trying to like actually predict the trajectory onto that new point. And if we move towards something like that, I could definitely see robustness being an issue.
And my last question is just about the equivariance problem. Do you think because one of the node features, two of the node features are the x position, the
Yeah.
position x and the position y, right? Do you
Mhm.
think that might have something to do with the equivariance problem or what?
Yeah, so so it is true, yes, that if you the XY values, if you rotate it, they change and your output changes, right? And so the way that I've been thinking so far of addressing this problem is more of like a pre-processing step. So a way, I'll just mention it briefly because this picture actually shows a way to account for it. There are many papers that try to account for equivariance, but I think that perhaps this is one of the simplest methods. Is what you can do is you can just do basically PCA on your cloud and then rotate the data so that it all aligns to one location. And so this is a way that, yeah, then if you do this, even if you're defining it with X, Y, I mean, if you're doing it in cylindrical, whatever coordinate system you're doing it in, I think you will have to account for it in some fashion. This is one way to do it. There are many people that try to set up, I think, networks in the way that they can account for equivariance in the sense that I'm talking about. But yeah, so far, I think this is probably the best way. And this will guarantee equivariance because all you have to do is shift and then shift back. Yeah.
Yeah, I see. Yeah, cool. Well, thank you very much for answering the questions. And again, very nice talk, very interesting.
Yeah, thank you
There
very
is
much.
another question from Bernardo. Alec? Okay.
Are you wanting me to just read off the question, or were you wanting for?
Oh, I mean,
Oh,
I can speak as well, no problem.
Okay. Yeah, thanks.
Hi, Alec, very nice work. I was just wondering about those GNNs, because so far it seems like everything is still free in the domain. You have all those vortices traveling around, and I was wondering if you can apply some external force in the system and still be able to predict where those vortices would go. For example, why aerofoil would interact with all those vortices, and how would this translate in your GNN, if it's possible to do that?
Yeah, so it should be possible. You can have like sort of global features outside of the graph that you can use in order to make predictions. And so I think that the way that you would implement it here, let me just show you like with these graph convolutions, a way that you could implement it, the first thing that comes to mind is it would just be very simple to like append the forcing as a constant
That's
nodal
what I
value.
thought.
So that would
Yeah.
be like a very easy way to do it. It might not be the smartest way to do it, but yeah, you definitely can add forcing like that.
And maybe the loss function would change because of that, I guess, or maybe not. You know.
Yeah, I don't think it would necessarily
Change
need
okay.
Unless unless there's something else you're wanting to predict other than the time dynamics when you apply the forcing, right? But I don't think it necessarily should have to change it.
Got it. Yeah. Oh, that's amazing work. Thank you. I really liked it.
Thanks, appreciate it.
Thanks.
Any other questions? If not, let's applause for Alec for the wonderful talk, and hope to see you in the next presentation next month. It will be around the time, I think late February sometime. I will be sending out the announcement for that. So thanks again, and hope you have a great time or rest of the day. Thank you.
Thanks. Bye, everyone.
Thank you, Alec.
Yeah, thanks. Bye.
Bye-bye.